for this part of the last of the semester. Today, I am very excited to welcome Professor Hadi Meidani, who is an assistant professor in the Department of Civil and Environmental Engineering at the University of Illinois Urbana-Champaign. His research focuses on uncertainty quantification, scientific and physics-informed machine learning, and class computational methods for infrastructure and engineering design. He earned his PhD in civil engineering and his MS in electrical engineering, and also an MS in structural engineering from the University of Southern California. And before joining UIUC, he was a postdoctoral scholar in the Department of Aerospace and Mechanical Engineering. So he's been over the place. I guess that's what we were doing. To some extent, yeah. And I look forward to hearing his talk. So please help me welcome Dr. Meidani.
Thank you very much, Daniel, for the invitation and for the introduction. Good afternoon. It's my pleasure to present some of recent research works on scientific machine learning with applications to structures and infrastructure networks. So this is the Bay Area network with millions of nodes and tens of millions of trips. Okay, so let me see if I can move this a little bit too. I don't think I can get rid of it, but oh, I can. I don't. There we go. Okay. All right. So this is the Bay Area network, has tens of millions of trips. If you're planning on testing different infrastructure projects, if, for instance, a bridge is going down for repair and you're wondering what is the effect of the network, you have to run a traffic assignment to capture the impacts and identify the trips that are going to be impacted. So here, for instance, we're showing the impact as the result of the closure of the westbound on Bay Bridge. And you see it's actually a substantial range of impact when you consider all the trips that goes or passes through the bridge. So the solution of the traffic assignment is going to take hours, if not days, on regular computers. So in order to really see what's going to happen as a result of different infrastructure projects, you are limited to a few scenarios because you cannot really consider various what-if questions. And as a result, you run a couple of scenarios and then you cross your fingers that nothing substantial exists there that you have missed. Now, in order to do a real what-if analysis and comprehensive study, you need to have rapid simulations and rapid digital calculations that can really help you run hundreds of studies and scenario analysis. Over in biomedical domain, the doctors have the same bottleneck. Take the mitral valve, for example. This is a very important part of the heart, which controls the blood flow between the left atrium and left ventricle. And the doctors, in order to come up with the best patient-specific treatment plan for a better performance of this mitral valve, for instance, whether they need to put in a ring or repair the leaflets. This is the top view of the mitral valve and how it works in one cardiac cycle. They need to understand the effect of their different treatment option for a particular patient. And this simulation, again, on a regular computer using a high-fidelity simulation is going to take tens of hours. And if they want to try different procedure scenarios, the window for planning or treatment planning may be gone. So civil, mechanical, biomedical, it doesn't matter. We always face the same bottleneck, computational bottleneck. And if we can somehow build a model that handles the variable geometry, variable loading conditions, variable environmental factors, you're using the traditional solvers, it's going to take a very long time for the simulation to be over. So here's on top is a typical design workflow. At the bottom, I have a typical resilience workflow. As you can see, the same story exists everywhere. So if you have the physics simulation box here, that takes a long time on top. And here it could be a traffic simulation or a traffic assignment solving equilibrium. This takes a lot of time. It lets you just do limited parametric study. And if you want to do uncertainty quantification, you cannot do it for a lot of different design variations. These are all the limitations that prevents you from having a really optimal design and optimal management plan for your infrastructure or structures. So the objective that we have is how to enable rapid simulation by learning the physics of the problem. So at the end, what we'll obtain is a surrogate for a high fidelity and expensive simulation that can give us the fast results with acceptable accuracy, and it can generalize to different geometry, different loading conditions, and so on and so forth. All right, so enter the scientific machine learning domain. This is the set of machine learning tools that are used for solving scientific problems. Typically, these scientific problems are continuous problems that are governed by partial differential equations, or network problems like regional urban networks, where the flow is again governed by some physics principles. So traditionally, we have numerical solvers where we solve physics. The governing equation was given by partial differential equations. So you had finite difference centuries ago, and then finite element, and the golden age of finite element and finite volume, where you could solve these problems. But again, time and simulation time was a big factor. They were very slow for complex problems. Now, more recently, in the late 2 decades ago, we are seeing improvements in the scientific machine learning models. These are machine learning models that learns the physics. So they could use results from simulation in order to understand how the physics of the problem works. So physics-informed neural networks, graph neural networks, and now neural operators are some of these techniques used in this domain. In this presentation, I'm going to present 3 scales of learning. The first one is physical laws. So you essentially use the simulation data in order to understand how the physics work and replace it with fast neural network-based models. Then networks, how a complicated relational behaviors can be learned by these neural network models. And then at the end, very briefly, on how you can invert these simulations and have a generative design procedure. So I'll begin with learning physical mapping from simulations. And I have here on the left-hand side a analogy from language models, large language models, where we deal with words and their embeddings and their orders appearing on sentences. So it's funny, when 2 years ago, I taught a course on large language models for scientific machine learning. And there I used a lot of examples from physics simulation in order to explain the language models. Now I feel like I have to use analogies from language models because everybody is so familiar with language models in order to explain what's happening on the physics side. So again, the way that language models process this complex or accomplish these complex tasks is that we have embedding for words. So they live in a vector space, and then the different words, depending on where they appear on sentences, there is a transformer architecture. We pay attention to different words in different ways. And then we have lots of training data. So the analogy here is that we have lots of simulation, well, a good number of simulation data that is our training set. And we have the embedding being like, for instance, the response being a function of like basis functions that are the last neurons on a neural network representation. And we want to train neural networks so that, for example, the pressure on the vehicle at different locations is given as a function of X and Y and Z, for instance. Okay, so the idea here is that the same way that we have different words appearing on different contexts, on different sentences, now here we want to see whether we can have a foundation model that can handle or predict the pressure, surface pressure on different geometry. So the goal that we have is a foundation model that is generalizable to different loading conditions and boundary conditions. On the left-hand side, I am showing you a fixed setting that is going to be used for a classical solver. You have a fixed location for a support, the loading, the material property, and you use a finite element model to solve it. But what if I want a single model that can manage and handle different material properties, different loading magnitudes, different locations for the support and loading, and different shapes of the domain? And if I am able to develop this foundation model or this generalizable model, then during the design stage, I can iterate over so many different geometries, and within seconds, I can calculate the response and decide whether that the design is acceptable or not. All right, so the foundation models that are offered in the literature, they're called neural operators. So the operator term is for when you map between input function and output function. So one thing that could vary is the geometries. So there are different ways that you could encode geometry in general among these neural operators. The first one is the grid-based operators, like Fourier neural operators, where you have a regular grid and you take, for example, the geometry or the input functions to the Fourier space and then process things in that space. So this is regular sampling and spectral learning. You have the graph-based neural operators where you have the finite element mesh. So you have nodes and connections between them that could come from a mesh, and you can process the model using a graph or topology structure and use the message passing graph neural networks, for example, to learn the geometry. Then you have the point-based methods, like the methods that work with PointNet or transformer or transsolver architectures. This is when you consider a number of points randomly selected over the domain, and then you process them. So these are three different classes of neural operators that exist today. And the way that these models work is that in the FNO or Fourier neural operator, what you do is to begin with an input function in that regular grid and then predict it on a regular grid on the output side. So that the left one would be a parameter, and then for example, the mechanical property, the right map would be the displacement or deformation. In the graph neural network, you do the message passing. Instead of doing a fast Fourier transform, you do the message passing between the nodes. In the PointNet-based or point-based methods, you do the MLP with transformer. You pay attention to different parts of the network, as we'll see in the next couple of slides. So our work has been focused on graph neural networks. We have a couple of papers on that for computational mechanics problems and also on point-based methods. So in the point-based methods, what you do is to sample the input function and sample the geometry and feed it into this two sides of the network, two parts of the network, and then for any new query points, you can predict the response. So this architecture is also referred to as a DeepNet-based architecture, where there is a separate path for a query location and also the input functions. So we had one of the contributions that we've done in this work was that this method is the original deponent was mesh dependent. So you have to have the same number of points. What we did here was a mesh independent framework where you don't have to always have the same number of samples from your inputs. And the geometry is same thing for the geometry as that and the input function. Okay. The other point here for this contribution was that it was suitable for physics-informed training. So this was a simple architecture that you could easily do backpropagation on, which is particularly useful for physics-informed training. And in case you have not heard about physics-informed training, it's a new paradigm, a different paradigm compared to the data-driven framework. So in a data-driven training, what you do is to predict the response using a neural network and compare it with observation. So you need to have observation in order to make the comparison and look at the error and try to reduce the error. In the physics-informed training, you do not have any observation or ground truth. You predict the response and plug it into the PDEs that you have and evaluate how bad or how much violation do you have in the governing equation and try to reduce that violation. So it's completely data-free. You do not have any labeled data for the physics-informed training. And of course, you could have a hybrid training where you use PDE laws and then data-driven laws and then combine them into the training. So that's in the parentheses what the physics-informed training is about. So we applied that work, and here is an example of how these models, a single learned model can work for different geometry, different material property. And you see that this is a plate elasticity problem, a plate with different hole sizes and hole locations. And a single model can predict a response. Okay, so so far we can train neural surrogates that respect physics, and they can generalize to unseen geometries and conditions. Now let us see some industry scale problems, some complicated problems, 3D problems that we can potentially solve. Here's a case study. This is a collaboration with Dassault Systems. So this is actually a car design. This is the mesh that you have from a car design. The mesh, the number of nodes on the surface of the car could be 100,000 nodes up to 1 or 2 million of nodes. So this is a very big input dimensionality. And using a CFD simulation, with a very time-consuming CFD simulation, you can calculate the surface pressure, which gives you the total drag force on the vehicle, and you want to change the aerodynamic design of a vehicle so that the drag is smaller and smaller. Okay, so we have developed neural operators for the fast prediction of the response, and you see the performance here. And this approach can really revolutionize the design, because for any new design iteration, you can quickly calculate the drag force and iterate over different design variations. Now, the way that we went about this was, again, borrowing these ideas from language processing and this notion of tokens. So a token on a language is each word that you have on a language, and then the transformer, which is based on attention mechanisms. What it does is that it figures the way that these tokens are interrelated. So if you're, for instance, predicting one of the words on this sentence, you know, for example, by seeing a lot of previous sentences, you know how much correlation exists between different tokens on a sentence. So this has been extended to the physics simulation, in the sense that if you have a surface geometry like this, you can break this down or do a segmentation over the geometry, 3D geometry, and have different tokens on the 3D geometry, and identify the best way that these tokens pay attention to each other. So the effective thing that is happening here is that instead of working with 1 million nodes and figuring out how these nodes are interrelated, you for instance, extract, let's say 20 different tokens. So it's almost like a hierarchical reduction technique that you do not need to process every single one of those nodes independently, but by grouping them together, it actually breaks down that curse of dimensionality and can help you with your learning performance. All right, so the work that we're currently doing is how to do that. So this is a segmentation that is purely data-driven by just trying different tokens and seeing which one better perform, results in better performance during the training. What we've tested is that you can also have some geometric information like the change in curvature and pre-process the data a little bit so that the task of tokenization later is easier for the machine. So this is human intelligence used in order to segment the nodal the nodes on the surface by looking at a relevant geometric information, which is the change in curvature coming from human intelligence, feeding it into the network and helping with the learning. And here's some of the very interesting performance metrics that we've achieved. First of all, the error is less than 1% relative to the finite element results. It takes 1 second, less than 1 second, to just do the inference for any new geometry to predict the surface pressure and the drag force, as opposed to 750 CPU hours that you would need for a finite element or CFT simulation to be completed. We have only used 4D training samples and tested this performance on 10 unseen data. What I'm showing here is the predicted pressure, total pressure, compared to the exact one coming from a CFT. And this dashed line shows the 1% error range, and you see that we're within that range. The blue one are the training data, and the red one are the unseen data. Now, of course, there are some challenges here. If you have a geometry that is very substantially different than this, typical sedan geometries, for instance, if you have a sports car, then you don't expect the same level of performance. So there is always an interplay between being out of how far out of distribution you could be in your geometry that you train. So this is the car. Yes.
When it comes to, are you theoretically speaking?
No, we haven't done any theoretical studies on this one. So this has been more numerical analysis. I'm trying to see whether there exists any theoretical analysis that is closest to this like transformer based. So I think it goes. Yeah, I haven't looked into that, but that's an interesting thing to explore. Yes.
I just have a question. When you're talking about different geometry, are you like parameterizing the geometry with like a few parameters and just like changing those parameters and see how this behave, or
very
like
yeah
like very general identification for it?
Very good question. So there are two different ways to input the geometry. One is a parametric input. The other one is non-parametric. Parametric input is, for instance, you have a family of varying geometries, but you know the underlying parameters. Maybe it's 20 different parameters that describes all these variations. That's a much easier task to do because you only feed a 20-dimensional vector and process it and learn it, right? These are all non-parametric. So we do not have access, the model that is trained doesn't know about the 20 or 50 different parameters that underlies these variations. This is purely non-parametric. So we only have the coordinates of the 200,000 nodes that we have.
So you are only modeling the what you have here.
Yeah, only the nodal values. So you have I showed you a very fine mesh on the other slide. So you have the coordinates, the 3-dimensional coordinates of those 200,000 1,000 nodes, and that's all that you process. Yes.
So these are when you say out of sample, is it basically out of sample in terms of just geometry, or you also plug in various boundary and input conditions?
Okay.
Is there dynamics involved in this?
Very good question. So for this particular one, we are only varying the geometry and the speed is constant. But you could also change the speed and boundary conditions. On the next example, I have an example of where the other boundary condition could be also different. Yeah, but in general, when you, so neural operators, they could include geometry variation, input functions, and so on and so forth. Yeah, and as a matter of fact, geometry variation came later. So the original neural operators, you have fixed geometry and you only vary the boundary conditions and properties, material properties. So here's another example. This is, again, essentially a patient-specific treatment planning. Even though it's the setup is a synthetic patient, so we don't have actual patient data, but this is with collaboration, again, with data systems and doctors. We created this set of data points where you have realistic virtual patient parameters, 17 in total. So this is where boundary conditions are varied in addition to geometry. So the geometry variation is one thing. The geometry at the initial condition at t equals 0 with 10,000 nodes, and this is non-parametric. Then there are parametric inputs also, which is the locations and properties of the mitral valve, and some of the boundary conditions. So you need to now process two things. One is a 17-dimensional vector. The other one is 10,000 node dot coordinates. And you want to train it. And then the prediction now is not a steady state prediction that you saw on the previous slide for the car. This is a complete cardiac cycle displacement. So what matters for these mitral valves is at the closed state, you don't want to have regurgitation where some blood flow is still can't go through. So it's very important that at the closed state, there is no gap. So this is, for instance, a mitral valve that is that's not doing the job that it's supposed to do. So so actually so in a way, the extension that we did on this work is to process both geometry variation, boundary condition variation, and do the temporal prediction. Again, I'm showing this side to side, the ground truth versus machine learning approach. That takes around 50 CPU hours versus less than 1 second. And you see very good correspondence between the two performance. Especially on the closed state, you see very good agreement between the results. So we're very excited about these results. And the current work that we have on this is some explainability, because it's very important to see what parameters the doctors, in terms of the treatment planning, how the solution or the surgery is going to look like, because there are different ways you can repair the leaflets in order to prevent this regurgitation, or there are different options like installing or putting in a ring. So that could also come from some sensitivity analysis or explainability that can go with this. All right, so some of the contributions here, the neural operators that we have developed with top performance on unseen geometry with irregular mesh. We have a paper where we have benchmarked all these different models on industry scale 3-dimensional models. So I think one of the goals that we had was to go beyond like simple 2-dimensional problems and handle larger scale 3-dimensional industry scale problems. We also did some multi-fidelity framework where you could use data from simulation that comes from different mesh sizes and maybe do some saving in the training stage by generating more efficient set of training samples. And we also showed how it can go through like cross-domain generalization, like by varying the domain geometry, you could still use these models, especially in the design process. All right, so the slides so far were focused on neural models that learn physics directly. Now we want to see how can we reason over and learn the physics over connected systems. Okay, so we want to move from local physics to network systems and use graph-based models to learn how connected assets behave collectively in order to achieve a certain system response. So the focus here is different in scale. It's on regional resilience. Okay, so the assets that we have that could be prone to failures due to natural hazards, they could be small scale or large scale. So it's important that we build the buildings and bridges that can withstand these extreme events, but also how we serve the communities by designing systems that can work in a robust and resilient ways to provide the services under the extreme cases. Now, there are different ways that we can approach the network resilience. So you could consider the hazard models to be earthquake or storm surge or flooding. And you have a transportation network that you're focusing on. There are different views that you can consider to define this notion of resilience. A classical view could be the topology only view, where you only, for instance, calculate the connectivity between different nodes, the betweenness centralities, notions from network theory that can be quantified under different cases. And that's one approach that doesn't, for example, in the case of transportation network, doesn't capture the traffic behavior or the transportation network modeling. So we've done some work on this area by considering earthquake scenarios. So here's briefly, I'm showing you the pipeline for that. This is a topology base where you calculate the connectivity probability between any given pair of nodes. And this is using a graph neural network model. So it starts by considering different earthquake scenarios, which leads to different fragility curves that you have for different assets, the bridges in particular. In this work, we focus on bridges. So the assets could fail with different probabilities under different PGA, peak ground acceleration. So you can then use that probability value in order to run a lot of Monte Carlo simulation. In some of them, the bridge is gone. In a lot of them, the bridge is safe. So you have to, if you are probabilistically managing the performance of this bridge, you have to run a lot of samples. And we've tested this framework where you get some samples from the high fidelity network-based connectivity algorithms and use and train a graph neural network where for any new earthquake, you do not need to do any network analysis. You just calculate the peak ground acceleration and the probabilities. Then you don't need to generate any samples. You just feed it into the graph neural network and it gives you the connectivities. And we have these performance results for different levels. We even tested the cross-network generalization, and the results are in the paper. You can capture the connectivity sometimes, even though you're close to a shelter location, for example, which is that red node over there. Even though you're close, because of the bridge conditions, you could see that, oh, the connectivity could drop for certain nodes that perhaps are connected to the target nodes using bridges that could fail with more probability. So these are all the insights that you could get that goes beyond only the individual bridge asset, but also capturing the connectivity between different nodes. Again, substantial, time saving, and the more detailed results are in the paper when you compare it with high fidelity network calculation. Now, moving from the classical view to have more detailed approach to resilience, you could have a data-driven view. This is a case where, for instance, you have sensor data and there is an earthquake or there is a wildfire in this case, and you want to build models that can predict the traffic flow under extreme cases. We have some paper that shows how to do this in a streaming online model updating in an efficient way. Sometimes the sensor is missing. How do you do data imputation when missing sensor is the case and you want to still make a prediction for the flow? Okay. So the point that I want to make is to make the case for physics-based resilience calculation. So data-driven methods are great because we have lots of sensor data. We can take advantage of them, but you need to have extensive sensor placement in all the network segments that you're monitoring and modeling. And you need to have accurate and healthy sensor data or correct sensor data in order to produce the correct performance. So if you have incomplete data, the OD demand could be incomplete, the sensor data could be missing in certain locations, then that's going to create some problems. The other thing is that if you care about the same idea of foundation modeling for this case, where we built a foundation model for different car geometries, the notion here would be to build a foundation model for different network topology. So if I train the model on this network topology and I'm considering a repair on a specific bridge, so the link is going to be gone. So there are changes to the topology. I want the same model to still be able to predict the performance for me. So I don't want it to be very specific to one topology. Okay, so this actually takes us to this physics-based approaches. So a very detailed one would be the equilibrium-based traffic modeling, where you have the principles of equilibrium, user equilibrium, and system-level equilibrium. There is the flow conservation. These are all the principles, physics principles that you can use in order to have the OD demand data distributed over the network, either in a static or dynamic way, and calculate the performance. It is the correct way to do this. It's the accurate way and precise way to do it, but it is slow. It takes hours or sometimes days if you're running them on office computers, if you want to have all the Department of Transportation engineers like run a lot of what-if scenarios. So how do we do come up with a new paradigm so that a single model can generalize across different network structures? You could run what-if scenarios, you could make changes, you could even apply a model that is trained on San Jose and test it on the city in San Diego, if more or less the size of the network is the same. How do you embed the flow constraints and handle missing information? So this would be the series of papers that we've published on how to learn network physics and be able to predict in a robust way the performance for varying topologies, missing data, and so on and so forth. All right, so again, similar to what I presented in the physics side, the paradigm is more or less the same. We use the data from high fidelity solvers. In that case, it was finite element. Here, it's equilibrium solvers. And we build neural network models that uses this data in order to learn what's the interrelationship between network topology, OD demand, and so on and so forth. So here is a fast model for traffic assignment problem, which is the equilibrium solver, which predicts the equilibrium flows given the OD demand and all these assumptions for the link behaviors. Okay, the challenges here is that if you're to use a neural network model, if it's non-graph-based neural network model, the generalization is limited because as soon as you remove one of these links, then the input data structure on the input is different. So you have to train a different model. But the graph neural network, because of the modularity, the structure that it has, it can manage different network topologies. So that's the good thing about the graph-based model, graph neural networks, for example. But the regular form of the vanilla graph neural network, the problem here is that there is a message passing involved in the graph neural networks where this node you predict the performance at this node as a function of the connected nodes. and you could do 2 hops so that you could go to the 2-hop neighborhood, but still it is local. What if this node is like you want to account for the origin destination information between 1 and 20? So you need to have several hops. And the more hops that you add in the message passing stage of a graph neural network, the more memory the memory burden you impose on the model, and the training becomes slower. So the idea here is to somehow integrate a different kind of long-range interaction into the graph neural network in order to still have a good performance. So then the other thing is different access networks for different vehicles and flow conservation. So I'll go over these few papers that we've had on this one just to show you the key contributions here. So as I said, in order to handle origin-destination relationship into the traffic assignment modeling, we added virtual links. These are not road networks, links, but just a link that captures the exchange information between the origin and destination nodes. And so the model is not a homogeneous model in the sense that links are only road links. There are 2 kinds of links in the graph. So here's a very, very busy figure of how this is done. But the key point is that you have real link features and virtual links, and they process together using the decoder and encoder architecture in order to predict the flows on different links. And here, so these are the performances. What I'm showing also on this plot is that we wanted to also test how robust this model is with missing information on the origin and destination. So we intentionally masked, like here, 20% of the OD data, 30% of the OD data, and 40% of the OD data, origin destination data. So in the training, while we were training these models. So we masked them in the test in order to see whether it can figure what was the actual unavailable origin destination data. And you see that compared to the other available approaches, which is graph convolution networks and graph attention transformer models, this is we're reporting better performance. So it's a very robust way of solving for the traffic flow. Yes. Yeah. Yeah, I didn't find a particular pattern. I think we did, I'm not sure if it's on this paper, but we did some synthetic networks. I think it would be interesting to test how does it behave if you have the same model to synthesize a network, but synthesize larger versus a smaller networks. Like how does it, so it could be actually a good experiment to run. This is another way where we have different network topology for access networks. So this is the network that is available to cars, network that is available to buses, networks that's only available to trucks. They're not independently processed because the background traffic data from cars should be seen here and vice versa. So there is the intra-view, which is interview and intra-view. So the intra-view, you only see what's happening here, but also you're paying attention to what's happening on the car side. So there are some exchanges, and we have some results on this. And then finally, this is a dynamic traffic assignment where the performance, so this is different times. So T1, T2, T3, and so on and so forth. So there are some exchange of information between these encoder outputs that goes as an input for the encoder on the next time step. So the idea is like an LSTM type architecture that is coupled with the graph neural network architecture in order to make this prediction. So here is the DTA, the results that we have for dynamic traffic assignment. Here we're showing an ablation study where we say, okay, if this is the proposed approach, if you remove the origin destination virtual links, the performance is gonna be worse because the error is gonna go higher. If you remove some of the link features, the roadway features, the performance is gonna be worse. So there are some, yeah, so this is essentially a relation study that shows that this proposed approach is the best one. Yes. Okay, so there on each node, so there are a number of features that you have. So for example, there is this node here, and then there is another node there. There is the link that connects them. The link has the distance, for example, right? So the physical roadway, you have the distance between the node that is a feature of the link, right? So if I'm here and there is a, for example, traffic flow here, and then there is a traffic flow there, then if I want to update the traffic flow here as a function of the other one, this link feature is gonna be used by the machine as an additional information for predicting that. So if it's a longer link or a shorter link, it matters for how this flow is a function of the other flow. Now, this is real network. Now, if you have here a destination and there is an origin, and you know that there is like this many cars that are supposed to go from that origin to this destination. So you want the flow that you calculate at this point to be also a function of that relationship. So coming from that origin to here, you want the prediction to also incorporate that one. If they are not directly related, the graph neural network is not gonna see that information, because that's information in the graph neural network approach is one as message passing. You have to have multiple message passing that information goes to the next neighbor, next neighbor, next neighbor. So it takes 10, for example, message passing for that information to be exchanged here and be used for this location. So the virtual link is inside the graph network architecture, the graph updating that we built. It bypasses this. So in one message passing, this sees the travel demand from that location. So it gets exchanged, the information gets exchanged instantaneously, as opposed to step-by-step procedure. Did that answer?
Flow constraint assignment. So we want to make sure that the sum of all flows between an origin destination here is equal to the total demand. So basically, something like that.
Yes. So the reason we have to do this inside a graph architecture, graph neural network, is that the graph neural network model is a local model. By construction, it is a local model. So it predicts the performance at this location as a function of the immediate neighbors. That's how this network, this particular machine learning model is set up. In order to make it non-local, you have to introduce additional long-range exchange of information, which is essentially what you just described, right? Yes.
So I guess
Yes, because the ODs are updated. Yeah, and that's an input feature. So these features are changed. All these are input features. At each time step, you have new input features. Yeah. So the new input feature comes here. The process version of the previous features are coming from here. Yes.
Have you also considered the physical property of equilibrium in the training of this network, or is purely based on data driven?
So do you mean the conservation laws? Okay, very good point. So we did for the training of, I think this one and the previous, the car one, we added a conservation term to the loss function. And it improved here. We see the residual is improved. Still, it's not 0. So the residual means the imbalance between the inflows and outflows. But it has improved this because it's what we call in the scientific computing is a soft assignment of constraints. So they're added as an additional penalty term. It's not guaranteed enforcing of the constraints. However, I think that's a good transition to this slide, where we, in this work, we did a different kind of training for a subset of links. So if you have 4 links coming to an intersection, it turns out if you only learn the 3 of those flows, the 4th one will be just a function of the 3. So what in this work that we did was we identified a subset of independent link flows and only learned those and calculated the remainder as a function of those. So the residual improved significantly, but what we observed was that since it's still a data-driven, maybe we picked the less important independent flows, so the accuracy dropped a little bit. So here, what we're doing is a balance between how much you care about the residual and versus accuracy. So if you care a lot about the residual, this becomes very small, but the accuracy is a little bit higher. And then if you relax it by 20%, the residual is going to be a little bit off, but the accuracy can be improved. All right. So again, was there another question that I missed? All right. So, okay. So in summary, these are fast graph-based digital twins for very rapid assessment of network response when you introduce changes, when data is missing, and so on and so forth. So, okay, I just close this by in a couple of minutes by showing that this can all be used in an inverted way in a generative design. So what we've done so far is somebody gives us an input design and then we evaluate. This is a rapid evaluation of the performance. What if you want to use it in order to automate the design generations too? So we've done some work on this. One is a topology optimization. This is a procedure where you do some training and then use the neural network in order to generate new designs. This is essentially showing you a two-dimensional L bracket under loadings. These are some sample candidate designs that we took, found an embedding space for this, which is a two-dimensional space. So each point that you find in this two-dimensional latent space is one design candidates that you can do. So you randomly select samples here, and then neural network maps it to this architecture and or topology. And as you see, it's you move away, and then they could be very different looking, depending on where you take the samples. So that can be used in order to generate the designs. And then we did a multi-fidelity approach where we trained a model for coarse designs, coarse scale designs, and refinements. And part of this network was used here in order to speed up the training. Another example of automated design is the design of metamaterials. So here is our work where we want to, for example, create a material geometry, which is repeated here. So we're interested in producing the best geometry like this in a repeated way, where there is a loading here, and you want to, for example, target this curve. So the idea is that this stress strain curve is given, and we want to design the best material for that. And you could do this by first doing a forward model, which is essentially trying to predict for a large family of shapes, predict the stress strain curves. And then once you have that forward one, then you can quickly evaluate the designs, but that's not the end of the story. We want to also generate new designs. So here is the forward models. For any design, you can quickly calculate the stress, but how do you generate new ones? That is coupled with the evaluation part. And here is work that we've used the diffusion models, which is very commonly now very widely used in order to generate new design. So it starts, I'm not sure if you're familiar with the diffusion model. So the idea of a diffusion model is that in the training, you start with a given object, you add noise to it to take it to a complete white noise, if you wish, and you reverse this process. When you reverse this process, you start with a random input, similar to that topology case. You start with a random input, and with this reverse procedure, you get to something like this, a continuous function. This is the sign distance function, and then you can generate deterministically from this a shape like this, and then feed it into this forward model and repeat this process. You can just draw new samples and repeat this over and over until you get the best performance. So here are some performance results that we're showing for the shapes that you're getting here. The target displacement, the target stress strain relationship or constitutive behavior is very similar to the exact finite element based solver. All right, so yes.
Some chemical properties.
Oh, no. So this is only the material shape.
I see.
Yeah. So this is you have the same material property. You want to build a component that can achieve this stress strain behavior. You want to see what should be the shape of it, and what's the efficient way of doing this. So you see that here you predicted you produce this and you produce that performance stress and strain distribution, and you pick the best one. Yeah. Okay, so the outlook and where this all can be headed is when we do the integration. So we integrate the simulation with the sensing data and the design. This would be a closed loop, right? So we are moving in that direction where you have integrated data-driven plus physics-informed and guided engineering systems. So this would be hybrid physical AI models that can also continuously learn from both data and laws, especially in transportation networks, which constantly there are changes that are happening, human factor. So it has to be an online and ongoing learning from both data and physics. So this would be an AI-assisted co-design where models, intelligent models and engineers iterate through different designs and finish that workflow. The challenges are the scalability. So how can we extend this to multiple physics, multi-domain, and multi-scale problems? For example, in the case of traffic flow, how do we also learn what's happening in the demand forecast? So if there is a major event, extreme event, the OD demands could be different. How do you build a model that captures that and is in sync with the traffic assignment problem and can simultaneously in a multi-physics or multi-domain way solve this problem? Trustworthiness, how do we quantify the uncertainty? It's an open-ended research question on how to quantify the errors and uncertainties in an efficient way for neural operators. Interpretability, how do you, especially with transformation models, these are very complex models. It's very important to be able to explain what's happening to engineers and decision makers for them to feel confident using it. And also integration, right? How do you integrate digital and physical experiments for continual learning and validation? With that, I thank you very much for your attention and we're happy to